Chapter 2, Matter. On a clear night in 1572, Danish astronomer Tycho Brahe had the opportunity of a lifetime. He noticed a new star in the sky. Over the following 2 weeks, the star grew brighter. Surprisingly, within 2 years, the star had faded from view. We now know that Tycho Brahe had observed a supernova, the explosive event that marks the end of the luminous phase of a star's existence. While a supernova is of immense interest to astronomers and astrophysicists, some chemists are also interested in these events. Many chemists believe that all of the elements in nature have come from the nuclear reactions in stars. Scientists understand that a star's energy is produced by nuclear fusion. Initially, hydrogen nuclei fuse to form helium. As a star ages, the nuclear fuel and products change until it produces iron. Iron has the most stable nucleus of any element and can't undergo nuclear fusion. At this point, a supernova occurs and propels both energy, up to billions of times the energy of the sun, and matter, the first 26 elements, into space. Along with these elements, the supernova ejects billions of neutrons. Iron can capture these neutrons and form higher mass elements. Secular scientists now believe that all of the other naturally occurring elements have formed through a series of neutron capture and nuclear decay events. The elements formed from those supernova events in the past supposedly went on to become planets, chemical compounds, and even living organisms. So are you stardust? 2.1, the classification of matter. 2.2, energy and matter. 2.3, the states of matter. 2.1, the classification of matter. In the chapter opener, you read a current hypothesis in which secular scientists attempt a naturalistic explanation for the origin of matter. While their model explains most observations about matter, they have no observable evidence for its origin, but they accept their model on faith. According to the Bible, everything was created out of nothing by God. A creation model for the origin of matter also explains almost all our observations about matter. We accept the biblical account on faith, and the Genesis account is the foundational truth of a biblical understanding of chemistry. Organizing our study of matter. The world that God spoke into existence contains an amazing variety of material. Just look around you to see the different types of materials and the things made from them: paper, wood, metal, plastic, computers, and cell phones. And these are just a few of the many forms that matter takes. Scientists have identified millions of different materials, both natural and man-made. Some materials may be in the same form as they were when created, but nearly all accessible natural minerals have been partially or even significantly modified by the Genesis flood. Humans also rework natural materials into other useful materials. Recall from Chapter 1 that matter is defined as anything that has mass and takes up space. With so many different types of matter, it would be good to organize our study of matter with a good classification system. Although there are different ways that we could classify matter, this textbook divides it into two major categories: pure substances and mixtures. We can make distinctions between these two categories on the basis of the physical and chemical properties of matter. Questions. Where did matter come from? What are some properties of matter? What are the different types of matter? Where did the names and symbols for elements come from? What do chemical formulas tell us? Terms: physical property, physical change; chemical property, chemical change; pure substance; mixture, heterogeneous mixture; homogeneous mixture; element, atom, chemical symbol; molecule, compound; chemical formula. Physical properties and changes. A physical property is any property of matter that can be observed or measured without altering a substance's chemical composition. Color, shape, texture, state of matter, odor, and taste are examples of properties that we can observe without changing the composition of the material. Other common physical properties of matter follow. What does it look like? How much is there? How closely is it packed together? Density. The amount of matter packed into a given volume is its density. Dense objects have a lot of matter packed into the space they occupy. Less dense objects have less matter in the same space. Density will be explored further in Chapter 3. Usually rocks sink because they are denser than water, but pumice, a volcanic rock, floats due to air trapped within its pores. Conductivity, the ability of a material to transfer heat or electricity between its particles, represents its conductivity. For example, the handle of a metal spoon left in a hot pot on a stove becomes hot, but the handle of a wooden spoon does not. The metal conducts heat easily. The wood does not. Silver is the most electrically conductive metal, but because of silver's high cost, we usually use copper for electrical wiring. Malleability. Materials that can be hammered easily into shapes or thin sheets are malleable. This property is possible because the connections between the particles that make up these materials are strong, but allow some movement. Most metals are malleable. 30 grams of gold can be hammered out to cover 30 square meters, more than the surface area of the family car. Ductility. Materials that can be drawn into long, thin wires are ductile. Ductility is another property of most metals. The same properties that make gold the most malleable metal also make it the most ductile. A single ounce of gold can be drawn into a fine wire that is 80 kilometers long. Copper and aluminum are also extremely ductile. The properties listed here are all properties that do not change, no matter how much or little of the material is present. For example, a material is ductile regardless of how much material there is. Properties such as these that do not depend on the amount of material present are called intensive properties. Other properties, like mass and volume, do change depending on how much of the material is present. These properties are called extensive properties. Physical changes are any changes in the appearance, shape, or state of matter in a material that do not cause a change in its chemical composition. Think about a ductile material like copper. As we draw copper into a long wire, it changes shape, but it is still copper. Boiling is a physical change in which a material changes from its liquid state to vapor, but its identity is not altered. Chemical properties and changes. Chemical properties are those properties that describe how matter acts in the presence of other materials, or how it changes composition under certain conditions. Some examples of chemical properties are reactivity, flammability, and toxicity. Reactivity. Substances can range from being completely stable to being highly reactive depending on the presence of other substances or particular conditions. Sodium is stable when stored in oil, but it will react vigorously in the presence of water. Water itself is an example of a material that behaves differently under different conditions. Water, typically very stable, will decompose in the presence of electrical energy. Flammability. While reactivity relates to how something responds to different substances or conditions, flammability is all about whether a substance will burn or not. We can burn hydrogen, demonstrating that it is flammable. When tested for flammability, hydrogen changes into water vapor through a chemical change. Also, flammability can depend on various conditions. For instance, metal zinc is not flammable unless it is in powdered form. Toxicity. Some substances have an adverse effect on living organisms. Toxicity indicates how much damage a substance will do to a particular organism. Toxicity is often reported as its LD50 rating. LD stands for the lethal dose, and the LD50 of a particular substance is the amount that would be expected to kill half an exposed population. Arsenic is a metalloid that is toxic to humans in very low doses. When a substance undergoes a change in which its chemical identity changes, we say that it has experienced a chemical change, also called a chemical reaction. When the composition of the substance changes, so do its chemical and physical properties. When iron rusts, it undergoes a chemical change. The iron particles combine with oxygen particles to form iron 3 oxide, Rust. Not only is rust a new substance, it also has different properties from oxygen or iron. Pure substances and mixtures. Scientists use chemical and physical properties to organize matter into pure substances and mixtures. Pure substances. A pure substance consists of only one type of matter. Scientists further categorize pure substances into elements and compounds. While elements cannot be broken down by chemical means, compounds can be broken down into elements through chemical changes. You will learn about elements and compounds later in this section. Mixtures. A mixture is two or more substances that are physically combined in a variable ratio. There are two types of mixtures, heterogeneous and homogeneous. A heterogeneous mixture consists of two or more materials in distinct regions, called phases. Consider oil and water. If left undisturbed, these materials will separate into distinct regions, the oil bubbles and water. Many salad dressings contain a mixture of vinegar and oil. No matter how vigorously you shake the dressing, a microscopic examination will always show two separate phases, oil and vinegar. Because of the different phases, heterogeneous mixtures typically have a non-uniform appearance. Scientists further categorize heterogeneous mixtures as colloids and suspensions, depending on the size of the dispersed particles. We will discuss colloids and suspensions in Chapter 14. A homogeneous mixture has only a single phase, which gives it a uniform appearance throughout. Homogeneous mixtures are also called solutions. If you dissolve sugar in water and stir it until it completely dissolves, it appears as a single liquid phase, sugar water. Likewise, when molten gold and silver are thoroughly mixed, a single phase of white gold results. Air is an example of a gaseous solution. Notice the soda, which is a solution, in the bottle at left. While it is a mixture, there's only one liquid phase visible in the bottle. Dissolved CO2 gives soda its fizz. Separating mixtures. Since mixtures are combined physically, they can be separated by physical means. The specific method used for separating a mixture will depend on the physical properties of the substances that make up the mixture. Some common methods of separating mixtures include filtration, decanting, and distillation. Filtration. When a mixture consists of a fluid and another substance with significantly larger particle size, we can separate the substances by filtration. As the small fluid particles move through the filter blocks the larger particles. Many of us are thankful for the common coffee filter that allows the liquid coffee to pass through while trapping the larger coffee grounds. Decanting. A heterogeneous mixture of two liquids or a liquid and a solid can be separated by decanting. We decant a mixture by pouring the less dense material off the top of the denser material. Traditionally, decanters were vessels from which wine was decanted, leaving solid sediments behind. Distillation. If the substances in a homogeneous mixture have sufficiently different boiling points, we can separate them by distillation. In this process, the mixture is heated until the lower boiling point is reached. As the mixture boils, it is collected in a separate container as a pure substance. The mixture is further heated until all the individual substances are separated. In the setup below, the mixture in the flask on the left will be heated to the boiling point of one component. That component is condensed in the central part of the apparatus and collected in the flask on the right side. Distillation is commonly used to separate hydrocarbons out of crude oil or to produce alcohols. We regularly deal with mixtures in our daily lives, but most of our study of chemistry will involve pure substances. Minilab. Paper chromatography. Chromatography is another method for separating a mixture. In paper chromatography, a sample is placed on chromatography paper, the stationary phase. The paper is then dipped into a solvent, the mobile phase. The solvent dissolves the sample. If the sample is a mixture, the solvent will separate the sample. The components of the mixture, as well as the degree of separation, enable a scientist to identify the mixture. Is the ink in a marker a mixture or a pure substance? Procedure. A. Straighten the paper clip so that it can span the beaker. B. Cut 3 1.5 centimeter wide strips of chromatography paper. The paper should be slightly longer than the beaker height. C. Pour approximately 30 milliliters of water into the beaker. D. Fold the top of each piece of chromatography paper so that the bottom of the paper will be just hanging in the water. Don't allow the paper to get wet. E. With a pencil, draw a line 1.5 centimeters above the bottom edge of the paper. F. On the lines you just drew, put a dot with each of the different markers that you have. G. Hang the papers on the clip so that the paper is in the water but the marker dot is not under the water. Cover the beaker with the watch glass. Why do you think the paper is the stationary phase and the solvent is the mobile phase? H. Remove the papers when the solvent stops moving upward or before it reaches the top of the paper. Mark the highest point of solvent travel. Conclusion. 2. Which of the marker colors was made up of a mixture of colors? 3. Did all the colors travel the same distance up the paper? Going further. 4. Why do you think the different colors travel different distances? Scientists use a measure called the RF value to compare the degree of separation of the different components. They calculate the RF value for a component by dividing the distance the component traveled by the distance the solvent traveled. Fifth, RF values provide quantitative data for the analysis of chromatography. How is this beneficial to scientists? Equipment. Beaker, 300 milliliters, watch glass. Paperclip. Chromatography paper, water-based markers. 3. Elements. In the description of the Garden of Eden in Genesis 2, gold is mentioned. Throughout the Bible, there are numerous references to many materials, such as silver, sulfur, tin, and iron, that today we know as elements. Scientists discovered many other elements shortly after the rise of modern science in the 1800s, and other elements have recently been synthesized in the laboratories of nuclear physicists. An element is a pure substance that cannot be broken down into a simpler substance by ordinary chemical means. Each element has unique chemical and nuclear properties. Today, there are 118 known elements that are represented on the periodic table. See table below. We also define an element as a pure substance that consists of only one kind of atom. For example, a piece of pure copper metal is made up of only copper atoms. An atom is the smallest particle that makes up an element and is capable of chemical interactions. An atom consists of a nucleus containing positively charged protons and, in most cases, uncharged neutrons. A cloud of negatively charged electrons surrounds the nucleus. When the number of protons and electrons in an atom are equal, the atom is electrically neutral. However, when they are out of balance, the atom has a net electrical charge and is called an ion. The particles of elements in their natural state may consist of individual atoms or groups of atoms. If an element occurs naturally as individual atoms, the element is called a monatomic element. Monatomic elements are rare because most atoms tend to bond with one or more other atoms. Examples of monatomic elements are neon, argon, and xenon. Elements whose atoms naturally bond into two atom units are called diatomic elements. The 7 diatomic elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Elements whose particles are normally composed of groups of more than 2 identical atoms are called polyatomic elements. For instance, sulfur often occurs in the form of 8 atoms bonded into a single unit. Oxygen can also exist as ozone high in the atmosphere. The subscript number in each chemical symbol shown at left indicates the number of atoms of the element that are present. If there is no subscript, we understand that the element exists in the form of uncombined atoms. Distinct groups of atoms bonded together are called molecules. Molecules may consist of atoms from one element or from different elements. Element names come from many different sources. Latin names serve as the basis for many of the symbols for some elements that were known in ancient times. For example, cuprum, the Latin name for copper, Cu, means from the island of Cyprus and is the source for its symbol. Elements are named after many things. Color, iridium, Ir, from the Latin for rainbow. People, curium, Cm, for Pierre and Marie Curie, early researchers of radioactivity. Places, Californium CF for California. Heavenly bodies, helium, he from Helios, the Greek word for sun. Miscellaneous words, bromine, Br from the Greek word for stench. Today, it is generally accepted that whoever discovers a new element has the honor of naming it, subject to the approval of the International Union of Pure and Applied Chemistry, IUPAC, an international organization responsible for standardization in chemistry. The periodic table of the elements in the back of this textbook displays the symbols for all the known elements. Compounds. A pure substance that consists of two or more elements chemically combined in a fixed ratio is called a compound. Some compounds form distinct particles, molecules, while other compounds form vast crystalline arrays with repeating arrangements of ions. As you can imagine, there are many more compounds than elements. Just as chemical symbols are used to represent elements, chemists use chemical formulas to represent the millions of kinds of compounds. The chemical formulas are made up of the chemical symbols for each element present. Numbers written at the lower right of a chemical symbol are called chemical subscripts. They indicate the number of atoms or groups of atoms in a chemical formula. A molecule of water contains 2 hydrogen atoms and a single oxygen atom, and so is written H2O. The 2 for oxygen is assumed. When a subscript follows a group of symbols that are surrounded by parentheses, it refers to the entire group. The formula calcium hydrogen carbonate consists of a calcium atom and 2 hydrogen carbonate groups, for a total of 1 calcium atom, 2 hydrogen atoms, 2 carbon atoms, and 6 oxygen atoms. Notice that the subscripts act very much like mathematical distributive property functions. The 6 oxygen atoms come from both the O and the O3. In compounds that form molecules, each molecule has a definite number of atoms. A molecule is the smallest distinct particle of a compound. Therefore, molecular chemical formulas indicate the type and number of atoms of each element present in each molecule. To illustrate this, let's consider 2 compounds of oxygen and nitrogen. The formula NO represents nitrogen monoxide. This formula tells chemists that each molecule of this compound contains 1 nitrogen atom chemically combined with 1 oxygen atom. Another compound of nitrogen and oxygen is dinitrogen trioxide, N2O3. This compound's molecule consists of 2 nitrogen atoms combined with 3 oxygen atoms. In compounds that form crystalline arrays, there are no distinct particles that make up the compound. Since there are no molecules, the chemical formula represents the smallest whole number ratio of the elements that are in the compound and is called a formula unit. Common table salt is a compound of sodium and chlorine ions in a crystalline structure. They combine in a 1-to-1 ratio, so the chemical formula for table salt is NaCl, indicating that for every sodium ion, there is 1 chlorine ion. Some common compounds, their formulas, and the atoms that they contain are listed in Table 2.1. Case study: Understanding trihydrogen. Trihydrogen is an interesting molecular ion consisting of 3 hydrogen atoms held together by a single chemical bond. Initially discovered over 100 years ago in 1911, trihydrogen has recently become of particular interest to astrochemists. In the early 1960s, it was hypothesized that trihydrogen could exist in the interstellar medium, the material located between stars. During the 1990s, its existence in the interstellar medium was confirmed, and by the early 2000s, it was noted that it existed in large quantities. Today, naturalistic scientists believe that trihydrogen was a key material in the transition from the origin of matter to the matter we see today. Questions to consider. 1. Of what is trihydrogen made? 2. What is an ion? 3. What does the existence of trihydrogen in the interstellar medium imply about the origin of matter?